Okay. Oh. Okay, say again about, well, we start again our class, all right? So what we cover? We cover the concept of optimization, okay? When we say optimization, of course, it's a course of action that you want to minimize or maximize some things under certain constraints, okay? Well, we will deal with that, and also we will deal with different types of mathematical programming. So what is mathematical programming? Is it different from computer programming? What do you think? Of course, when I say computer programming, I hope that everyone know what it is, right? But when I say mathematical programming, what is it? Do you have any idea what is it? What do you think? Mathematical programming.
It's about the process of doing math to seek optimal solution and control.
Okay. Yeah, it's of course, when we say computer programming, what is programming? Program, you say that, well, you know that we have a series of command, right? You send some command to interact with computer, right? But in case of mathematical programming, we don't have CPU. We don't have agent to take care of that things, right? When we say mathematical programming, we mean the action of a formulation from real world problem. Of course, for real world problem, you want to optimize something, you want to minimize something, you want to maximize something, which subject to certain constraint. Then you have to, represent all those things, your problem, in a mathematical form, right? And that is mathematical programming. Okay. And the class also extends to the concept of convex, non-convex programming. Okay. And you know that, you know TX programming. Always we say programming. When we use the word programming, that means that is mathematical programming. Okay. And it is, in other words, we also know that it is optimization problem. You know, linear optimization problem, from time to time, we use the word linear programming. Okay. Also, convex, non-convex programming, it is convex optimization problem, actually. So you can replace the word mathematical programming with optimization problem. Is it the same things? And while we extend the course to cover global optimization, okay, and practical application in chemical engineering. Okay, now it is the time to understand the optimization problem. Okay. Well, one definition of optimization is the process of finding the best solution. Well, we use word best. Why don't we use maximize or minimize? We use best because sometimes you want to minimize it. Sometimes you need the maximum solution. Okay, so we use the best, the word best, to represent the solution you want. Okay, but the important things is constraint. We have a certain set of constraint. Okay, you want to find your best solution in which also satisfy the constraint. Okay, so even the solution has smaller value and you want to minimize it. However, those solution does not satisfy the constraint. It is not our solution, okay? So we will define the optimization problem and discuss different types of optimization problem, okay? And we also introduce the idea of function to be minimized or maximized, okay? And explain why optimization is useful in real world scenario. So while let me show you the importance of optimization problem. We can think the optimization is a game changer, okay? When it's come to efficient use of resource, okay? Or use for cost minimization or profit maximization across various fields, okay? So, well, you may heard about the decision making process. What is decision making process? In everyday life, you know, we have to make a decision, right? Whether you want to buy this, buy that, you want to go or not go, or well, everything is decision, right? So this good strategy for decision making, you need optimization, okay? And every time, well, if you're dealing with decision making, you deal with optimization problem, okay? I will show you how optimization can be used in different applications. For example, supply chain management, production energy system, or chemical process. Okay, now we know the optimization, okay? The concept of optimization, okay? We can treat the optimization as an effective tool for decision making. Consider that, well, you want to go somewhere, for example, yeah, this is a map, right? And I believe that you are familiar with this kind of map, right? If not, well, you can turn on your Google map, right? And you want to go somewhere, okay? You mark it and you mark your current location. Okay, you want to find the best way to somewhere, maybe, well, the fastest way from here to the Grand Palace, okay? So what you want when you open the map and look for Grand Palace, how to go to Grand Palace, what is our objective in this case? The fastest way, right? So what does it mean, fastest way? You want to minimize the traveling time, right? Travel time from here to the Grand Palace, okay? And you have a set of constraints. For example, you have only 100 baht in your pocket, so you cannot spend more. For example, you have, I don't know, what is your constraint? We have, yeah, number of constraints in everyday life. Okay, so this is an example of optimization problem. Our objective is to minimize the time, travel time, right? Or you want to find the cheapest way to reach Victory Monument from here, okay? And of course, your objective is minimize the cost, right? The fare. And subject to resource you have, set of constraints, for example, well, the time, you cannot spend 2 hours from here to Victory Monument, something like that. And now it's becomes the travel time becomes a constraint, right? Okay. Let me show you another case. Okay. For those who are living with family, maybe you, well, it's not related to you. However, if you stay alone, okay, you're on yourself for buying goods from supermarket, something like that. Yeah, you're familiar with this shopping in supermarket. Well, to achieve the best option relative to set of constraint, it's our optimization, right? Well, which goods to buy in a limited budget, okay? You have certain amount of money, right, in your pocket, and you want to buy goods, okay? And you see that you have to make a decision what to buy, right? Okay. And of course, we need objective. You want to buy something. I don't know what you want to buy. A drink or food or I don't know. But you have a series of constraints. Okay. Or in a supply chain problem scenario, what and when to stock up goods. For example, you decided to run a shop, okay, maybe drugstore. And of course, you have to stock medicine, right? Before the customer come, right? Okay. Then what medicine and when to stock those medicine becomes your solution, right? Okay. And of course, you have a series of constraints. Or in our chemical engineering field, when you design a process, you need design parameters of the plant, right? For any process you're designing, okay? You have to list all the design parameters, and your target is to find those optimal design parameters, okay? So you have to set the objective, what you want, okay? And then list all the relevant constraints. Okay. In other case, in case of operation, where we have already built our plant, we have process, the process is already there, and you want to operate it effectively, efficiently. Well, you have question on what to produce, okay? And which operating parameter should we set? And that becomes decision making again, and optimization problem again, okay? So now we move to the structure of optimization problem. Okay, now you have concept of optimization problem already. Okay, now concept of the whole process, I mean decision making and optimization. Okay, so we deal with optimization problem. Okay, and this is the simplest structure of optimization problem. The problem of minimizing or maximizing function subject to a number of constraints. Okay, we write minimize or maximize like this way. Okay, when we write minimize, we want to minimize what? Minimize this function, and this function we call it objective function. Okay, now you learn objective function. When we say objective function, that is we want to minimize or maximize the objective function. All right. And what is here? X here. This X we call decision variable. Okay. So we want to minimize objective function by adjusting decision variables. Okay, we adjust X in order to minimize fx. Okay, and you notice the relationship between decision variable and objective function. Objective function must be a function of decision variable. Okay, always objective function should, well, be a function of decision variable, so that when we move the decision variable or we change the decision variable, our objective function change. Okay. What else do we have in this structure? We have constraint. The first one, well, we write ST. ST is standing for subject to. Okay. The first type of constraint is inequality constraints. Okay. You can have multiple constraints, of course. Okay. And we have equality constraint. Okay. Inequality or equality. What is the difference between equality and inequality constraint? The difference lies on this relationship. Okay. For inequality constraint, it must be lesser or greater. Okay. Lesser or equal, greater or equal. Yeah. And for equality constraint, yeah, the name is equality, right? So it must be equal. And you see that decision variable also plays important role here. Okay, because the constraints also function of decision variables. Okay, so you see that when we change, we change the decision variable, it affects the objective function as well as constraint. Okay. Do we have a case that the objective function is independent of decision variable, but only constraint are function of decision variable? The answer is yes, we have such a case. Okay, and in some case, we don't have constraint at all. Okay, we have only the objective function and decision variable. Okay, but the most important things for optimization problem is we need objective function. In some case, you don't have constraint. It's all right, no problem. However, if you don't have objective function, we have problem. Okay, because it's not objective optimization problem. Okay, if we don't have objective function. Also, if we don't have decision variable, yeah, it will be a problem, right? Because we cannot adjust anything, right? So the most important things here are objective function and decision variables. Okay, so the optimization problem consists of objective function and constraint. That in short. Okay, equalities, inequalities. And if we look at the optimization problem, in a viewpoint of degree of freedom, I will tell you. But let me explain the concept of degree of freedom first. For degree of freedom, what is degree of freedom? What do you think? I ask someone here, maybe Pai. What is degree of freedom? Yeah, you learned process dynamics last time. We have, I introduced the concept of degree of freedom. No. I mean, in general, what is the degree of freedom? Not here. I mean, yeah. What is the degree of freedom? The simple answer, it's maybe, well, a number of variable we have, but the variable must be independent variable, right? And subtract with relationship. Okay, and the rest is degree freedom. Okay, but the physical meaning of degree freedom is how many variables you are free to adjust. Okay, for example, what is this? This is a case of degree freedom is less than 0. Is possible? Yes, in some case, but it signifies something. Degree freedom is less than 0. That means, well, we are not free to adjust anything, and the problem is over-defined already. Okay, for example, we have a domain of 2 variables, x1 and x2. We have only 2 variables available, right? And they are independent, right? x1 and x2, you can choose freely without f1, f2, f3. Yeah, you can choose any place. But in order to choose any place, you need to specify 2 parameters, right? 2 variables, x1 and x2. Okay? And I give you one line, maybe f1, only f1. Once I give you one line, f1, and I tell you that, while you can choose anything, any point, but you must satisfy f1. What does it mean? You see that f1 define the relationship between x1 and x2, right? So what's the problem? What is the degree of freedom we have now? Only one. We start from a blank domain, right? Domain of x1 and x2. And you see that you can freely choose any point, but any point specified, defined by 2 variables, x1 and x2. But once I give you f1 and tell you that x1, x2 must satisfy f1, you have only 1 degree freedom. Why? Because you cannot choose this point, that point. You can choose x2, but x1 is defined by f1 already. Okay? Or you can choose x1 and x2 is defined by f1 already. Okay? So that means you are free to choose only 1 variable at a time. Okay? That is the concept of degree freedom, right? And if I give you 2 constraint or 2 relationship. For example, f1 and f2, I give you 2 relationship, f1 and f2, and tell you that, well, your solution must satisfy f1 and f2. What is the degree of freedom this time? 0. Because you cannot choose anything, right? The solution already defined by f1 and f2 here. Okay? What about this case? I give you another relationship. For example, f3. Okay? So degree of freedom becomes negative now, right? Because we have two variables, but we have three relationship, right? 2 minus 3, of course, it must be negative, right? If my memory serves, right? Yeah. So degree of freedom is -1. So if I ask you how many degree of freedom we have -1. -1 means, well, the problem is already over defined. Okay, you ask too much, you over define the problem, right? Okay, and in such case we don't have solution. Okay, because most of the case those constraints conflict with others, right? For example, in this case we cannot have any points satisfy F1, F2, and F3 at the same time. Okay. Okay, good. Well, you may have a question. Is it possible that we have solution? For example, if we move F3 to pass through this point, the intersection of F1 and F2. Yes, it's possible, but anyway, degree of freedom is negative. Okay, because it's overdefined. You don't need this F3 in order to specify this point, right? F1 and F2 are enough. Okay, enough to define the solution. Okay, if we have question from online, you can ask me anytime, right? Okay. Now we move to a case of degree of freedom is 0. Actually, I should start my slide from what's it? Degree of freedom of 2, right? And then degree of freedom 1 and degree of freedom 0 and then negative. But it's all right. You understand it. It's okay. Yeah. Degree of freedom is 0. That means the number of relationship equal the number of free variables. We have two variables, right? Free variable, x1 and x2. And we have two relationships. Where is F1? Yeah, this is F1 and F2. Okay. And it's, yeah, already defined the solution. Okay. What about this case? Degree of freedom is greater than 1. Degree of freedom is positive. The number of relationship is less than the number of free variables. Okay, we have x1, x2, okay, as independent variables. We have two independent variables, and we have only one relationship, F1. Degree of freedom is 1, right? That means, well, you can freely choose x1 or x2, but not both at the same time. Okay. Okay, so how this thing, how degree of freedom related to, we move, related to our optimization problem. In case of optimization problem, we can treat the optimization problem as a system of equation with degree of freedom being greater than 0. Okay. Why? What does it mean? Look at the constraint. If we have equality constraint, one equality constraint define one relationship, right? That means it consumes one decision variable already. Okay. For example, if we have two decision variables, we have to choose 2 points, x1 and x2, and you have one relationship. For example, F1 in the previous slide, you see that it consumes 1 degree of freedom, right? So our degree of freedom is 1 in that case. Okay. Or we don't have constraint at all. We have 2 degree of freedom, right? if we have x1 and x2. Okay. And what happened if we have two equality constraints and we have two decision variables? We don't have degree freedom, right? So the problem becomes system of equations. You don't need optimization problem anymore because all the constraints already define the solution. Okay. Or in some case, we have too many. We have constraint. A number constraint is higher than the number of these variable. And you can say that, wow, that is overdefined, right? It's not optimization problem again. Okay. You need algebraic, okay, to solve the problem. You don't need optimization in such a case. Okay. The only one scenario that we need optimization is when the number of constraints is less than the number of decision variables. Okay. Got my point? I see some question mark in your face. Yeah. Any problem? Any question?
Repeat that again. The content have to be less than the number of the
Decision variable. Okay. Yeah. We look at this. When you have animation, you see that it's very slow. Okay, so remove, yeah, imagine that we don't have F1, F2, F3, okay? We have only domain of X1, X2. And you define the objective function. What does it mean? We want to find X1, X2 that yield the minimum, the smallest value of objective function, okay? However, if I give you F1, yeah, remove F2, F3. Okay, only F1. Now you optimize, minimize the same objective function. You have one constraint, right? But this time you see that you cannot freely adjust X1 and X2. Okay, you can adjust only X2, or you can adjust only X1. Because of what? Because if you adjust X2, X1 must satisfy F1, right? And that is still optimization, right? Because you are free to adjust one variable. You can adjust one variable until you reach the minimum point of objective function, okay? But if I give you another constraint, F2, your solution must satisfy F1 and also F2. What happens now? You are not free to adjust anything. You don't need optimization anymore. Your objective function is useless, okay? Because the solution must satisfy the constraint, okay? And now, if I give you another, the situation becomes worse, right? Because we want a solution that must satisfy F1, F2, and F3 at the same time, right? And most of the case, we cannot guarantee that, okay? In such an overdefined problem, okay? Okay, good. We move to next things. Yeah, actually, I should speak slower, right? Maybe I speak too fast. Okay, so we will deal with classification of optimization problem, okay? Why do we need the classification of the optimization problem? because you know the structure of optimization problem, right? And later you will know, you will learn how to formulate such a problem, such a optimization problem from real world problem. Okay. And after that, we will learn how to solve the optimization problem. Okay. And we have number of optimization problem. I mean, various types of optimization problems. Of course, each type of optimization problem require different algorithms. Okay. No such super algorithm that can solve everything. Okay. Of course, some algorithm can solve more than one type of optimization problem, but for effective solution, I mean solver, yeah, we develop some algorithm target at specific types of optimization problems. Okay, so the first thing, we can classify the optimization problem based on the existence of constraint. The existence of constraint. Well, you remember the structure of the optimization problem. What do we have? Minimize or maximize objective function, and we have decision variable, right? And we have ST, subject to constraint, list of constraint. We classify the optimization problem based on the existence of constraint. If we don't have constraint, it's very easy to solve. Okay. We call such a problem as unconstrained optimization problem. Okay. And in opposite way, if we have constraint, it's straightforward. We call it constraint optimization problem. Okay. Which one is easier to solve? Unconstrained optimization is much easier to solve. Okay. Well, some case, of course, it's actually it's useful, nothing useless. I mean, why do we need unconstrained optimization problem? Because real world problem also always come with constraints, right? Everyone has constraint. So why do we need unconstrained optimization problem? Yes, we need it. Because in some case, if we study in that area, we can guarantee that the solution is far from the constraint. The constraint is already there, but you know that your solution is far from such a constraint. In that case, you can treat the problem as unconstrained problem, because unconstrained problem, optimization problem, is much easier to solve. Okay. Okay, so then we move to the next one, classification of the optimization problem based on the nature of design variables. What is the nature of design variable? Oh, wow. Previously, I told you that it's decision variable, right? In some case, no, people use it's, yeah, decision variables or design variable. I can tell you that they are the same things. Decision variable or design variables. Okay, you can call anything decision variables and design variables. You can call anything. Yeah, people know what you are meant to. Right? Okay, so the point is we classify the optimization problem based on the nature of design variable or decision variables. Now look at the design variables or decision variables. Sometimes your decision variable can take only integer. Sometimes it can take, yeah, any continuous variable, any real, okay, real number. but sometimes it can take only integer. Okay. For example, if I design the distillation column and the number of tray is my decent variables, I cannot build a distillation column with 1.5 or 10.5 tray, right? It must be integer. Okay, so you see that it poses different type of optimization problem already. Okay, if we're dealing with integer, we call such a problem as integer programming or integer optimization problem. Okay, and which one you can you guess which one is easier to solve between integer programming and non-integer programming? Huh? No, in the opposite way. Integer is much difficult, right? Because if it's not integer, it's a real problem. You can your decision variable can take any value, right? You don't need a condition to specify it as an integer. Okay, but if it's integer, you need special algorithm to deal with it, right? To handle such variable. And where we are now. Okay, and another thing is parametric optimization problem or static optimization problem. Okay, we minimize objective function, right? Then our objective function is a function of this variable and another variable, which is not adjustable, but is not static. It can take any value in the distribution, okay, with certain probability, maybe. It can take any value from probability distribution function, something like that. Or it can take as an uncertainty. It can take any value in this range, something like that. Okay. In this case, we call it, yeah, it's a uncertain optimization problem. It's not static, of course. Okay. And what about parametric optimization problem? For parametric optimization problem, this value is, of course, it can be adjusted, but it's not this variable. It's some value that we want to find the solution, which is a function of this parameter. Okay, it's a new parameter. Okay, maybe difficult for you to follow this time. Okay, but later we will cope with this. It's parametric optimization problem. Okay, so the next classification is based on physical structure of the problem. For example, optimal control problem or non-optimal control problem. This is interesting for control guy. Well, for example, considering if you are design plant, okay, you have design parameter, right? And those takes up as your decision variable, right? But once you formulate optimization problem and got the solution, well, that is a static value, because you want, while certain number of the maybe tray number, certain value of diameter, something like that. However, in case of optimal control, it's not static. It's a profile of something. Imagine about the controller. For controller, you measure For feedback control, you measure the output, right? And then your controller have to adjust the manipulated variables, okay? And of course, process evolve, and then you measure again the output, and then your controller adjusts it. And you see that if we formulate such a problem as optimization problem, your controller need a solution which is a profile, not a certain value, right? Because, well, our solution is, well, at this time we adjust manipulated variable at this value, and then the other time, the next step size, okay, next sampling time, we adjust the manipulated variable again and again, okay, as a series. And you see that this kind of problem is dynamic in nature, okay? So you can expect that the objective function or control or constraint involve the ODE or PDE, okay? Differential equation, okay? Okay, so now we move to the thing which is easier to understand. We can classify the optimization problem based on the nature of equations involved. For example, if your objective function is linear function and your constraints are all linear, we treat the problem as linear programming problem, okay, or linear optimization problem, okay. In short, we call LP, linear programming. Of course, if your objective function is not linear or constraints are not linear, the problem becomes nonlinear programming problem, okay. Well, either case we have geometric programming problem or quadratic programming problem. For example, quadratic programming problem, the objective function is quadratic function, but the constraint is convex function, something like that, okay. We will talk with this thing later, okay. The next thing is classification based on permissible values of desired variable. Oh, this one, yeah, I already tell you what is it. Real value programming problem or integer programming problem, okay? When your decision variable can take only integer, okay? Or your decision variables can take anything, real value. And the next thing is classification based on deterministic nature of variables. I think this one also I explained to you already. When all the parameter in optimization problems is already defined, we call it deterministic programming problem. However, if some parameter, of course, it's parameter, not decision variables, those parameters are stochastic. It contains uncertainty or variability. The problem becomes stochastic programming problem, okay? For example, if you want to minimize the, what's it? Your distillation, crude oil distillation, okay? But you know that the oil price is fluctuate, okay? You can formulate such a problem by taking into account the variability of the oil price, something like that. Yeah, and it becomes stochastic programming problem. Okay, the next thing is classification based on the separability of the function or classification based on the number of objective function. This one is interesting, classification based on the number of objective function. Yeah, on the left hand side, we call it single objective because we have only one objective function. All right. You need a solution which yield minimum value of fx. On the right hand side, we want to minimize f1 and at the same time minimize f2. Okay. This becomes another type of optimization problem. Okay. We call this type of problem as a multi-objective function optimization problem. Okay. Or multi-objective optimization problem. Okay. In real world, most of the time we deal with multi-objective optimization problem. You want, your objective is minimize cost and at the same time you minimize other things, something like that, or maximize other things. Okay. And the solution for, what is the solution in case of multi-objective? For multi-objective, of course, if we plot between objective 1 and objective 2, okay, f1 and f2, we see that if the objective function is conflict, for example, the first objective function is conflict with the second objective function, we end up with a non-dominated front. We end up with number of solutions. We call this front as non-dominated front. What does it mean? Here we want to, minimize objective 1, and at the same time we want to minimize objective 2. We cannot say that this point is better than this point. No, we cannot say that. Because of what? Because here, in terms of objective 2, this one is better, right? But in terms of objective 1, this one is better. So we call it non-dominated front. Okay? So in this case, our solution becomes a set of solution which is non-dominated in the non-dominated front. Or we can call it non-dominated set or non-dominated solution. Okay. But if you look at the, oh, actually I should not point there. Yeah, because it's not recorded. I should sit here properly and move my cursor instead. So it will be recorded. Sorry about that. Okay, so we see that this point and this point belong to non-dominated front, right? However, if we compare this point with this point, you see that this point is dominated by this point, right? So it's not our solution, right? Because if we consider both objective 1 and objective 2, this point is better in both objective function. Okay? And that is the concept of non-dominated front, which is a solution of multi-objective optimization problem. Okay, so we have a summarize of types of optimization problem. The first one, continuous versus discrete optimization. For continuous optimization, the decision variables can take any real value, right? Real number. However, for discrete, the decision variable can take only the integer, right? And while the next classification based on the deterministic versus stochastic optimization, where deterministic means all the data is known. Okay. In stochastic optimization, some data is unknown. Okay. or contains variability. And the next one, convex versus non-convex optimization. Well, this one, for convex optimization, we are dealing with a convex set, okay? And of course, what you have question is, your question is, what is convex? Convex function. Later, I will explain you what is convex function, okay? Convex and non-convex. And the last one, we can classify the optimization problem as linear or non-linear optimization, okay? In the old paradigm, we classify roughly the optimization problem as linear and non-linear optimization problem, because linear optimization problem can be solved effectively using, of course, certain algorithm. However, later the paradigm shift, because we learned that even convex, even non-linear optimization problem, however, as long as the constraint and also objective function still convex set, we can solve it effectively also, okay? So for convex programming, it's a special form of optimization problem where the optimization variable are assumed to be continuous. The first thing is your variable must be continuous first. Okay, all the decision variable must be continuous, cannot be integer, right? And the objective function is convex function. Okay, later I will show you what is the convex function. Okay. Okay, and I will show you I will explain to you the convex set and convex function, and what is convex optimization problem, also how to solve convex optimization problem effectively. And while we will deal with non-convex programming, but non-convex programming is a form of the optimization that involves non-convex function and also constraint, non-convex constraint, okay? And this is very large class of optimization problem, and it's much more difficult to solve compared with convex optimization problem, okay? We will examine the challenge in solving non-convex optimization problem, okay? And the next topic is mathematical programming. Well, mathematical programming methods used to solve the constraint optimization problem. Okay, both objective function and constraint are known and expressed mathematically. Okay, we start from problem definition first. We define the problem. From real world problem, we define it. Okay, and the meaning of problem definition is, sometimes we call it formulation. Okay, problem formulation. We map from the real world problem to optimization problem. We call it definition, problem definition of problem formulation. Okay, once we obtain the optimization problem, then we move to algorithm or the strategy to solve the problem. How to solve such a problem? Once we can solve the problem, we obtain the solution, okay? And those solutions will be implemented in the real world problem again. Okay, that is the concept of the mathematical programming. Okay, so we start from modeling and solving optimization problem. The first task is formulate the optimization problem, okay? Which is a mathematical representation of the real world problem. For example, if you design a plant, okay, you have to formulate the objective function. What is your objective function? For example, you want to minimize NPV. What is NPV? Pardon? Huh? Net present value. Okay. You have to write down the net present value of the process as a function of decision variable, right? In a certain period of time, but because you use NPV, in NPV, the element of time become significant, right? Okay, so you have to define other thing like interest. Okay, you need interest rate, right? Okay, and if you think that interest rate is not constant, it can be fluctuate. Depends on the, of course, the economic. Yes, which is true. We can formulate as a stochastic problem where the interest can be varied. Okay. Then example. Okay, then what we need from the formulation of the optimization problem? We need accurate representation and also in an efficient form. In an efficient form. Okay. And we need accurate representation. Why we need accurate representation? Because you want to, well, because we are going to represent, right? Formulate the mathematical problem to represent real world problem. So we need, well, accurate representation in that case in order to effectively represent the real problem. Okay. And why do we need efficient form? Of course, if it's, well, most of the time, accurate representation, you have to trade off with efficient. Because for accurate representation, maybe your problem is very difficult to solve. Okay. Your function is very complex. Okay. But you have to trade off, right? For example, you know that your process is nonlinear. It's nonlinear means, well, it's not linear. But to represent the problem accurately, you need nonlinear function, right? To represent your process. However, nonlinear function is, of course, is really difficult to solve. More difficult to solve compared with linear function. Okay. So you see that you need some trade-off. Okay. Once you formulate the problem accurately, formulate the problem, the real world problem as optimization problem in an efficient form, of course. The next task is you must solve the optimization problem formulated. Okay. But you have to consider what solver available. For example, if you have convex optimization problem solver that can only take the convex problem, of course you cannot solve the non-convex problem. Okay. If you want to solve the non-convex problem, you have to invest more on solver. Okay. And you see that before you formulate the optimization problem, you have to consider resource you have, what solver you have. You should formulate the problem in a form that you have solver, your solver can solve. Okay. And the next things you have to consider is tractable solution. What is tractable solution? For example, you need a solution in 1 hour, because you have to adjust the operating parameter every hour. That means you have to formulate and solve the problem within 1 hour, right? But the problem you formulate, also the solver you have, can solve the problem in 1 day. We call it, this is not tractable solution at all, right? Because you take 1 day to solve the problem, to obtain the solution, but you need the solution in 1 hour, okay? So you have to consider that. Also, in some case, for example, optimal control problem. As I mentioned to you that we can use optimization as a controller, okay? You solve optimization problem and you have to implement those manipulated variables, okay? You obtain from the optimization problem. You know, controller have to implement every 1 minute or 2 minutes, or even smaller than that, okay? Shorter than that. But most of the time you obtain the solution, you solve the solution in 1 hour, okay? But you have to implement something. You have to adjust manipulated variable. In that case, it's not tractable solution, right? If you need solution in 1 minute, of course, the whole process must be finished within 1 minute, right? Okay, so you have to consider if your optimization problem and also your solver is tractable or not, okay? And the next step is, once you obtain the solution, you have to interpret the obtained solution, okay? Why do we need the interpretation of the obtained solution? Because you see that the optimization problem we formulate is solely the abstract of the real world problem, okay? It's not the same problem, right? Because during the course of formulation, problem formulation, we assume something, okay? And because we need to represent the problem in an efficient form, okay? So once you obtain the solution, it's only the solution of the abstract or the solution of the formulated optimization problem, okay? So you have to interpret the solution first, whether the solution is, well, can be used or satisfy the real problem or not, the real world problem or not, okay? If not, you have to go back to the formulation again, okay? Adjust the assumption again, relax some things, or, well, change the form of your function, something like that, okay? And most of the time, it's required the problem reformulation. Okay, any questions? Any questions on that? No? I forgot to tell you that we have quiz. We have a pop-up quiz. But it's okay, just enjoy it. Don't take it so serious, yeah? Okay, so we move to the problem formulation. The first thing is we have to define the objective function. Our objective function is we want to minimize some function, right? Minimize or maximize the objective function, right? So different objectives will probably lead to different optimum solution. You have to think about that, okay? And possible objective function that might be suggest for optimization as follow, okay? you can formulate your objective function as profit. And most of the time we maximize profit, okay? Or if you want to change maximize to minimize, of course, it's very convenient. You just minimize negative profit. It's the same thing, right? You multiply profit by -1, okay, -1, and then you minimize. It is the same thing, okay? Maximize profit or minimize negative profit. Or minimize cost or maximize negative cost is the same thing. However, maximize profit does not equal to minimize cost, okay? Because it is different function. But in some cases, it's the same thing. If your revenue is constant, of course, you maximize profit or minimize cost, you obtain the same solution. Okay. And the next one is maximize utility, maximize turnover. It depends on your problem. I cannot tell you which is the right objective function. It depends on the problem. But this is only example. Maximize return on investment. You know, return on investment, right? Maximize NPV, okay? Minimize redundancy. In some system, you know, you have redundant process, right? Backup process. Yeah, you want to minimize redundancy to save the cost, something like that. Or maximize customer satisfaction. I don't know how to formulate such a problem, but some people do. Yeah. Maximize probability of survival. Okay. I never work on that kind of problem, but some people do on that. Yeah. Maximize robustness of operating plan. Operating plan, sorry, not plant. Operating plan. For example, you have a number of uncertainty. Okay. And you want to maximize robustness. Okay. What else? Well, previously I mentioned to you that we have case of single objective function or multiple objective function, right? Multi-objective function, multi-objective optimization. Okay, so for single objective, well, it's quite straightforward. You select one objective and then you formulate the optimization problem, the objective function, okay, based on the objective you choose. Okay, minimize that or maximize that. Okay, but in case of multiple and conflicting objective, you will obtain it result in multi-objective optimization problem. In this case, you can write this way: minimize, okay, of fi x, where I can be 1, 2, something like that. You have two objective function. It's minimize f1 and minimize f2 at the same time. Okay, and you have these variables. And the solution for multi-objective function, multi-objective optimization problem, remember that the solution is a non-dominated set or non-dominated front. Okay. And the next one is minimax objective. This is quite interesting and it takes some time to explain it. I think we can break it now for 10 minutes and we come back with explanation of the minimax objective. Okay. Okay, so we take 10 minutes break. Oh, welcome back. So, yeah, I hope everyone's ready. We stop at this point, right? Minimax objective. Okay, we have minimax objective function. Well, actually, you can, at first, when you see minimize and maximize here, an objective function, at first you think that, well, what is the difference from multi-objective function and minimax objective? I can tell you that it is a bit different. What we have for multi-objective, you see that we have number of objective function, okay, conflicting objective function. However, in case of minimax, you see that we have single objective function. However, we maximize objective function by adjusting y. Okay, and we have another set of object decision variable where we target at minimize the objective function. Okay, you see that we have two sets of decision variable, right? X and Y. The first set, X, target at minimizing the whole value, the objective function. However, we adjust Y to maximize this one. So we see that it is minimax objective function. Then, well, I will, of course, I can explain you several applications using minimax objective function. For example, in robust control, we deal a lot of, minimax objective function. I will try to, explain in, very simple application of this one. Okay, so think about if we have, say what is, okay. If you have data from experimental, you have experimental data, like, well, for example, you have this, even this, okay. And this should be X and Y, right? Oh, sorry. X and Y. Wait, we don't want here. We need X and Y. Okay. Oop. All right. So where you can see, right, from the back of the room, you can see it clearly. Okay, good. So you see that we have experimental data representing the relationship between X and Y, right? It's very formal that for engineering and science that we want to find the how Y is a function of X, right? So we write Y is a function of X, okay, this way. And because we don't know this function, but if we look at the data, the results, the experimental result, you can see that it is somewhat linear function. Yeah? Do you agree? It's a linear function, right? It looks like linear function. Of course, you can use exponential or quadratic, but it's much easier to use linear, right? Okay, so So we agree that we are going to write this relationship as linear function. We have mx plus c. Okay. And if we look and if we want to represent this relationship as linear function, you see that we need two parameters, two variables. The first variable is the, what is it? The slope, right? Which is related to m, right? You adjust m, you adjust the slope. Okay. What about c? Another parameter. You adjust c, you move it to the left or to the right because you adjust the intercept, right? So you adjust m and c at the same time, right? In order to achieve minimum deviation, right? For example, this is one snapshot. I mean, one representation of this. I should use no screen. Yeah, the blue. Okay. For example, we have this is one possible solution with certain m and c. Okay. And you see that how we classify, how we define whether our estimation is good or not. Because good approximation must yield smallest error, right? What is error? Error is this, I know. Yeah, you know, this is error. Any deviation from the prediction. Okay. Of course, if we adjust M and C, it will lead to different error, right? Are you with me? Okay. So the simplest way is if we write this as E1, E1 represent error from the first point, E2, E3, and so on. Okay, EI, right? And you know, deviation can be positive or negative. But either way, they are error, right? We don't want both positive error, positive deviation, or negative deviation, right? Okay, so we can formulate optimization problem as minimize what are our decision variables. Cartoon, huh? What are our decision variables in this case? No, error, it's not decision variable. Error, it's just performance, just objective function, right? What you wanted to adjust? And yes, slope and intercept. Slope and intercept. So we have M and C. All right. You can write A and B, but well, the same thing. You can write anything. But here I write M and C. What? M and C. All right. So we adjust M and C. M and C is our decision variables. With certain set of M and C, we obtain different error, right? And error must be, we consider only positive value of deviation, right? There are two ways to make it positive. The first one, you square it, okay? You wow squared, or you take absolute, okay? For example, we have EI, right? Square. But remember that we have E1 to EN endpoint, right? So we have to summarize it. Summarize all square error, okay? Or you can minimize okay, good. Right? So what is EI? EI is EI defined as YI subtract by MXI C. Okay? You can write this way. Also, this is important, right? For both representation. Yeah, EI is deviation from prediction and from the discrepancy between prediction and result in experimental data, right? So you see that what we know from experimental data, we have a set of Xi, Yi, right? So we have Xi, Yi already, okay? And each point, of course, because M and C change, so it affects EI, right? EI change based on MC. And that EI here, you plug them here, right? So what we're going to optimize, we minimize square error or absolute error. No, sum of absolute error or sum of square error. Okay. Do you think that by solving this problem and this problem, do you think we obtain the same solution? When we say solution, in this case, is a set of M and C, right? Our solution is M and C. Do you think we obtain the same solution? No, impossible, because we use different representation, or we define different performance, different sum of error. You see that if some data point is far away from the prediction, it will be penetrated by square, right? Much larger than absolute. Okay, so in average, of course, absolute is all right. Okay, however, if we choose to use this one, if we have outlier, outlier, right? Some data point which is really far away from the prediction, resulted from error, resulted from typical error, we call outlier. Okay, if you don't filter the data first and you allow such a data which really large discrepancy, it will affect the performance of prediction, right? Okay, so how this thing related to minimax? Remember that at the first place, we are discussing about minimax optimization, right? But here, until this point, up to now, we haven't touched any minimax yet. But I'm going to tell you the minimax optimization now. Okay, so from here, you see that we adjust M and C, we adjust the slope, right? The slope and also the intercept in order to obtain the smallest sum square or smallest absolute error. Okay, so, and I told you that the weak point of this one is if there is a point which is much lie on, if we have outlier, for example, here, outlier here, you see that, well, most of the points can be well predicted. However, this one will penetrate the book. How can we undo this? Okay. Okay. However, this one affect the prediction, right? Another, alternatively, we can predict the system in order to minimize the maximum deviation. No, minimize the maximum deviation. Yeah, right. We want to find the MC, which is our decision variable at the first place, in order to minimize the maximum error. You got my point? That way, we need minimax optimization problem. What is the minimize the maximum? You see that we have the maximum error here, right? This is the maximum error, right? So, but in practically, we don't know at the first place which one is the maximum error, but we want to minimize that maximum error. Okay, so we can formulate the problem this way. Minimize. Oops, I did something wrong. No, okay. We want to minimize the problem. Oops. Yes. Why? What's wrong with this? No. Okay, max I. Okay. Of EI. We try to minimize the maximum error. Okay. And we have to be sure that all the error must be positive. All the error is positive. So, no, sorry. Absolute error, just absolute error. It's a positive now. So EI is this deviation from YI and MXI minus C. Yeah, this way. The constraint is not a single constraint, of course. We have number of constraints depends on the number of data point. Okay, the concept is we minimize the maximum error. Okay, but this formulation, of course, it's if you understand the way we formulate it, you can capture the abstract, what we want. But for solving this problem, it's not easy like that. One way to solve such a problem, we reformulate the the problem again from minimax optimization problem to single objective optimization problem. We formulate this way. We, what is it? Maximize or minimize? It's just one moment. Minimize, right? We minimize M and C to delta. And we have to be sure that, we have to ensure that all the absolute error less than delta. This is one thing. And yeah, this way guarantee that delta must be positive, right? But we can write delta again. Delta must be positive. And we need, of course, the EI is YI minus psi. Let's see. This way. This is our representation, new representation. This one is not minimax optimization problem, but it is a result from reformulation of minimax optimization problem. Okay, you understand the concept of minimax, right? But what we formulate here, you see that we set the maximum error. We call that maximum error as delta. Okay. Oh, I should include delta as a decision variable also. Sorry. Oh. No. Okay. Delta. Okay. We create a new variable delta. What is delta? Delta is defined as the maximum error. And you see that we try to minimize the maximum error, okay? Because we minimize delta, right? We minimize M and C, also we minimize delta to ensure that the maximum error is minimum, okay? And delta, because delta is maximum error, so all the absolute value of EI must be lesser or equal delta, right? Here, we define here. Absolute error, each absolute error must be lesser or equal delta. And the next line is delta must be greater or equal 0, must be positive. Of course, it must be positive, right? Because it is the maximum error and our error is positive. So we force them. We force it to be positive. Okay. And the rest, you understand it. I believe EI is deviation from the experiment and predict value. Okay. So from minimax, it becomes the single objective and you can solve it. Okay. Okay, this is one application of minimax optimization problem. Okay, I think this one is well, easy to understand, because if I rest the problem, minimax problem for robust control, it will be more difficult. In optimal control, we use it to represent the, because we want to find the parameter, the control action, which minimize the deviation between set point and output, right? However, our problem contains variability or disturbance. We have disturbance all the time. We don't know, but we know that disturbance can be, well, between certain range. Okay, so we can formulate the optimal control problem as minimax by we minimize the error, the deviation between set point and output by adjusting the control action. However, we consider the maximum error. So minimize control action and maximize by adjusting the disturbance, the deviation, the offset, something like that. Yeah. But this one is much easier to understand, I think, for the minimax optimization problem. Okay, any questions on that, on this part? Because if not, we move to another item. No? Okay, all right. So back to our slide. Okay, so I explained the minimax objective function already, right? Minimax objective optimization problem. And the next one is ratio objective. In some case, imagine that you are dealing with multiple and conflicting objective. But you have only two objective functions. For example, you want to minimize F1 and at the same time maximize F2. Minimize F1, maximize F2. Okay? Then you see that if we divide it, we take F1 and divide by F2, F1 by F2, and you want to minimize F1, maximize F2, it becomes single objective function, right? Okay. Then we call ratio objective, that case, where, we want to minimize F1 and maximize F2. So if we make a ratio of F1 to F2, it's the same thing. Okay. And the last one is non-existing and non-optimizable objective is useless. Okay. The next one is defining constraint. We define the objective function, right? Which is the important cost for mathematical programming. Now we move to constraint. The constraint can be formulated by using productive capacity constraint. For example, your process the capacity of your process. For example, your distillation column can take only 1,000 tons per day, 1,000 barrels per day, something like that. Okay, or your reactor can operate at maximum 100 kilomole per day, something like that. Okay, and it poses the constraint of the system for the system. And remember that we have two types of constraint. The first one is inequality, and the second one, equality, right? For productive capacity constraint, do you think we should formulate it as inequality or equality constraint? Nấm hòm. It should be formulated as equality or inequality constraint for productive capacity. Inequality? Equality. Okay, what happened if we formulate it as equality constraint? For example, we are planning the operation for distillation column. Our distillation column can take 1,000 barrels per day. Okay. So if you write as a equality, right? Equality constraint, you have to operate at 1,000 barrels per day all the time. Is it correct? Do you think? No, we don't care about that, right? As long as, for example, our objective is profit, we want to maximize profit. As long as the profit is maximum, we don't care about operation, right? As long as it's not reach the maximum. It's not reach, not exceed the maximum. Okay, so it should be inequality, right? It should be less or equal maximum capacity. Okay. The next one, raw material availability. Raw material availability is what is it? For example, yeah, the same case, distillation column. You can purchase crude oil from any country, yeah, but maximum you can buy at most 2,000 barrels per day, something like that. That is availability, right? Raw material availabilities. You operate, you take gas from Gulf of Thailand, and of course it has a maximum capacity, right? We call it, in our viewpoint, we call it raw material availabilities, right? So in this case, what do you think? It should be equality or inequality constraints? Prince? Huh? No. I ask you, wait up. Should we formulate raw material availabilities as equality or inequality constraints? Huh? Why equality? Everyone loves equalities. Should be inequalities. Yeah, you can buy at most this value, but you don't have to buy that value, right? For example, you buy something from the market. You want to cook any food, I don't know. Yeah. And you visit the market. It's available in the market. You can buy meat from market. Do you have to buy all the meat available in the market? No. Okay, except you have some contract with them that you have to buy at this value for this amount. Okay, but in most cases should be inequalities. Okay. The next one is marketing demands and limitations. This is interesting. Marketing demands and limitation, what is it? Demand of the market. You know that your market size about that, yeah? And you have some limitations on that, right? This one can be equality or inequality. Why? Because most of the time, when you enter anything to market, you need contract. You need contract with your downstream that you have to supply them at least this certain value. If not, you have penalty or something like that. But if you don't have such a contract, of course, it can be inequality constraint. Okay. However, you have contract, you have promise, then it must be equality constraint. Okay. The next thing is material balance, or we call it continuity constraints. What is material balance constraint? For example, while input, whatever you feed to the system, it must be agree with the output, right? It's material balance, of course. This must be equality, always equality, right? Equality constraint. And it's not only material balance, energy balance also, okay? Or you have some correlation, thermodynamics correlation, or kinetic correlation. These things must be equality constraints. Okay? You cannot violate material balance. If you can violate material balance, well, I guarantee that you fail everything. Okay? The next thing is quality. Quality stipulations. For example, you produce ethanol, and your ethanol must be, the purity of your ethanol must be greater than 99.9 something, yeah, and the rest 0.01%, it can be anything. Okay, this must be inequality constraint. No one cares about, well, even your product must be at this certain purity. No one care, but the quality must not lower than that point, right? Must be greater or equal that point. So it should be inequality constraint. And the last one is hard and soft constraint. This is interesting because hard and soft constraint, it's well, you will see that on dynamic optimization or optimal control problem, where we have hard constraint and soft constraint. For soft constraint, of course, it can be violated for certain period of time. But for hard constraint, you cannot violate the constraint anytime, right? The constraint must be satisfied all the time, okay? But for soft constraint, violation for a certain period of time is possible. Okay, the next one is chance constraint. This one also interesting, and you see that in stochastic optimization problem. What is P? P is standing for probability. Probability that this constraint is satisfied must be greater than certain value, something like that. Okay, what does it mean? It means that you have, because your problem contains variability, right? Some uncertainty. And if you check your constraint, probability that this constraint is satisfied must be greater than certain value, something like that. Okay. 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 So how to build a good model? Okay. Model in this case is applicable for optimization problem also, and other model also. Okay. The first thing that you should consider is of understanding the model. Okay, you formulate the model, must be, well, must be easy enough to be understood by other people, okay, or yourself, because while the time you work on the model, and maybe 1 week later, if you look at the model again, if you formulate it, it's very difficult. It takes time in order to understand the model again, even written by you. Okay. The next thing is as of detecting error in the model. Okay. You should write the model such that the error in the model can be easily detected. And as of computing the solution. Okay. As I told you that, mathematical function, you can write in a different way, of course. Even linear function, if you divide linear function with linear function, it becomes non-linear function, right? And you should avoid that because linear function is much easier to be computed, right? So you should write your model as much as easy enough for computing. And the last one to be considered is units of measurement. I guarantee that, we talking at the first place that, everyone should consider units of measurement must be in agreement, even in the same problem, Sometimes you use inch, sometimes you use millimeter. That is not a good practice, right? You should use the same. You should use consistent unit of measurement. Not only measurement, but other things. You should use the same unit, okay? Consistent unit. I think we will talk this slide very fast because I'm going to tell you what tools we are going to use. The first one, we will use MATLAB. MATLAB is standing for, do you know what is MATLAB standing for? Yes, metric and laboratory. Yes. So you can imagine that the engine of metrics, MATLAB works on metric. Okay, it's very efficient on metrics. Yeah, we will use that. And luckily, you don't have to use. No, we have license for MATLAB. Okay, just figure out how to obtain the license. Don't buy the license by yourself because university provide that. Okay, not university, faculty of engineering provide that already. So yeah, please install it by yourself. Also that also we use YALMIP, YALMIP. Yeah, I call it YALMIP. What is YALMIP? YALMIP is a toolbox, okay, for user-friendly modeling interface. Okay. YALMIP is not solver. Yeah, one thing. You need solver. YALMIP is just only the interface. It's a model interpreter. Okay. You write the code in YALMIP, and YALMIP will transform it in a way such that it can be solved by other solver. Okay, and it works. It works in MATLAB. Okay, what happens if we don't have YALMIP? Can we solve the problem? Yes, if you have solver. But the problem is, for different solver in MATLAB, you have to learn the syntax. how to write the command, efficient command for each solver. But if you use YAML, YAML will take care of that. You use the same pattern, the same code, and then YAML will select the available solver to solve it. So I encourage to use YAML. Okay, it can be download and then install inside MATLAB. Okay, and you need some solver. I will recommend you what solver. Beside MATLAB, we will use Excel. Okay, Excel solver. Excel is a great tool, especially for linear programming. Okay, the power of linear programming is, well, it's sensitivity analysis. It's not on the solution. Okay, we will discuss how to perform sensitivity analysis, okay, inside MATLAB. What else? Yeah, this one. Gurobi optimization. This one is a tool. It's a solver, sorry, solver. Optimization solver. It's solver for, it's very efficient for mixed integer programming. Linear programming, of course, and mixed integer for convex. You can download it, and Gurobi offer a free license for academic, for personal use for 1 year. You just, wow, go to their website, download, install, read the README how to, yeah, and also apply for license. Okay, just check it. Because this is a solver. We need this solver to solve mixed integer problem. Okay, and it works with YAML and MATLAB. Alternatively, if you don't want to use MATLAB, YAML, you can rely on Python. Python offers several tools for optimization, but sorry that I will not cover it in this class. You can visit CVX PY for Python, and yeah, this one PYOMO, PYOMO. You can work by yourself. Okay, we will not cover it, but it's great tools. This one, it's all right. You cover later. Okay, so now it's a great time to enjoy the quiz, our quiz. Yeah. So boss, online and on site. Yeah. You can put this QR code. I move my cursor first. Or you can type it by yourself if you want. Okay, we have Pai here, we have Beam, we have Pat, we have Meme, we have, I don't know, what is it? With ID number. Cham, Ink, yeah, Supawat, Cartoon, Ta, and Cat. Everyone in? Now 16. น้ำหวาน Samson okay Saha Ram Prince okay good so everyone ready เจมส์ไม่เข้า you are in Oop. It's a quiz online quiz yeah you can drawing your avatar also while we're waiting you can playing game all right everyone ready yeah we have 20 people in the system you know well of course I will not use this mark for grading but yeah I hope you pay attention to it because the winner will get some prize okay ไม่มันถ้ารออยู่มันมีเกมยังไม่สตาร์ท okay ready 21 people here okay so we have 10 questions not start yet I explain first okay so we have 10 questions and each question we have 4 choice you can choose and you have 1.5 minutes for each question all right so we start now yes okay the time is running out now 8 6 5 2 1 okay yes okay so wow I should show you the all 3 of you did not answer why why you don't answer all right 88% and the correct answer is yes on C okay 11% sorry yeah sorry about that but the correct answer is C minimizing or maximizing some objective okay Whoop. Okay next activity which of the following best describes a constraint in an optimization problem And the correct answer is, yeah, B, a limit or restriction. Okay, most of you got the right answer. And three did not answer. I don't know why. Who are those three? Okay, so who is the leader? I beam Pat, no, David. No, you still have 2000. All right. The next one. Yeah, it must be linear. Yeah, in linear programming. Okay. Okay, so okay, we still have 0 people. Which of the following problems can be solved by optimization techniques? Tập linearไง. Yes, 100%. Mm. ข้อต่อไป I did not explain the feasible region yet, but you can guess, I think. Oh, okay. The right choice is the set of solutions that satisfy all constraints. Okay. We are halfway now. Beam. บีมออนไลน์อ่ะบีมอยู่ออนไลน์ Okay, next question. Which of the following is not a type of mathematical programming? approach the last. A local minimum, a point where okay, so the last one, in optimization, a local minimum is a point where the value of the function is lower than that of nearby points, okay, but not necessarily the lowest. And the winners, Beam, Cham, and Ta. Yeah. Okay, you will get your prize next week, okay? Hmm? What? อะไรนะ คืออะไร คืออะไร อ๋อ โอเค Okay, so while we going to finish our we're going to finish our today class. Yeah. Next week we will move to the real problem. Of course, it's not real problem. It's still abstract of something. But I will try to give you different definition of real world problem. And then we will work together to understand what we have, what information we have, and then formulate the objective function, formulate the constraint, list of all constraints. And what else? And write this way, of course. Yeah, this mathematical programming that we want. If you have installed, if you have MATLAB and YAML available, then we will try to solve it, okay, in MATLAB. Okay, good. So any questions? Any more questions for today? I hope you enjoy. We will have more quiz next week, okay? All right. So any problem, any question? No? Okay, so well, enjoy the rest of the week, okay? Now today is starting, huh? Over. Yes, Monday is holiday. So one moment. Yes, Monday is holiday. So well, I will record the video, okay? And then you can take your time, you study at your pace. Okay, and then we will come back on 21st, right? 21st, yeah. Either online or on site, it's okay. Depends on you. And for today video, I will post it in YouTube, and then well, you can later check it out. Okay. Okay. Have a good day for everyone. So what to do? Stop sharing first, right? And then it. Okay. Online people also. Okay. Enjoy the rest of the week. Bye bye.
Bye. Thank you so much.
Bye bye, teacher.